Hello everyone. So in today's video, I'm going to check out and try to learn probability using this Think Based 2 by Alan B. Downey. This is an insanely good GitHub repo which I had found randomly, and he has all the notebooks which he uses on Collab as well. But I'm going to use the website which he has put up. So let's just start off the preface. I'm not going to focus on the preface because it focuses more on how to like sort of set it up and who it is for. I need to revise this up, so let's just dive right into it. So the foundation of Bayesian statistics is Bayes theorem, and the foundation of Bayes theorem is conditional probability. Okay, so in this chapter we'll start with conditional probability, derive Bayes theorem and demonstrate it using a real data set. In the chapter, we'll use Bayes theorem to solve problems related to conditional probability. In the next chapter, okay. So let's start with this example, Linda the banker. To introduce conditional probability, I'll use the famous experiment by Tversky and Kayman, who posed the following question. Linda is 31-year-old, single, outspoken, and very bright. She majored in philosophy. As a student, she was deeply concerned with issues of discrimination and social justice, and also participated in anti-nuclear demonstrations. Which is more probable? Linda is a bank teller. Linda is a bank teller and is active in the feminist movement. Okay. So many people chose the second answer, presumably because it seems more consistent with the description. It seems uncharacteristic if Linda is just a bank teller, right? It seems more consistent if she was also a feminist. Okay, that seems reasonable. But the second answer cannot be more probable as the question asks. Suppose we find 1,000 people who fit Linda's description and 10 of them work as bank tellers. How many of them are feminists? At most, all 10 of them are. In that case, the two options are equally probable. If fewer than 10 are, the second option is less probable. But there is no way that the second option can be more probable. Alright, okay, so I can think of a way to visualize it using the entire space of Linda and like a Venn diagram, and then you have a circle for the bank tellers. So let us just kind of draw it up. So yeah, so if this is a circle representing all the bank tellers, and then at max you can have like some sort of intersection, right? These are the Lindas which fit the description and are feminists. So only this portion, which I'm going to shade now, where are the brushes? So this portion, the intersection portion, is the satisfying region. So at max, this can be equal and never be greater. That makes sense. So if you were inclined to choose the second option, you are in good company. The biologist wrote, I am particularly fond of this example because I know that the second statement is least probable. Yet a little homunculus in my hand continues to jump up and down shouting at me, but she can't just be a bank teller, read the description. If the little person in your head is still unhappy, maybe this chapter will help. Okay, that was quite a good introduction. At this point, I should provide a definition of probability, but that turns out to be surprisingly difficult. Okay, oh, so there are tons of interpretations. So let's just stick to what he's going to tell us. To avoid getting stuck before we start, we will use a simple definition for now and refine it later. A probability is a fraction of a finite set. Okay, that makes sense. For example, if we survey 1,000 people and 20 of them are bank tellers, the fraction that works as bank tellers is 2%. If we choose a random person from this population, then the probability that they are a bank teller is 2%. By at random, I mean that every person in the dataset has the same chance of being chosen. Okay. With this definition and an appropriate dataset, we can compute probabilities by counting. To demonstrate, we'll use the data from the general social survey. Okay, so it's using pandas to get the data. So every person has a year, age, uh, sex, political views, party ID, and industry. So I'm not really sure what do they represent. So let's just have a look at this survey. Maybe this will. Okay, there are. This is the respondent ID. Year when the respondent was surveyed. Okay, the age when they were surveyed. The sex, male or female. So I guess one of them is male and two would be the other one. Political views, okay, on a range from liberal to conservative. the party ID, and the code for the industry that the respondent works in. Makes sense. Okay. The code for banking and relating activities is 6870. So we can use pandas to get like, okay, there are 728 bankers in our data set. So to compute the fraction of bankers, we can use the mean function. Okay, so approximately 1.5% of the respondents are bankers. So if we choose a random person, the probability that they are a banker is this. Makes sense. So now he's creating a function to compute the probability. So if you give a particular occupation, it returns what the probability is. Okay, so now one was male and two was female. So if the probability of female is being checked, it is 0.53. So the fraction of women in this data set is slightly higher, okay, is higher than the adult US population, because the GSS does not include people living in institutions like prisons and military housing, and these population are more likely to be male. Okay, political views and parties. So the other variable, extremely liberal, liberal, slightly liberal, moderate, slightly conservative. Okay. So if the political view is less than equal to 3, so he is a liberal, slightly liberal or extremely liberal. So we get that about 27% of the dataset was liberal. Okay, so we get what he's coming at. So now the conjunction. Now that we have a definition of probability and a function that computes it, let's move on to a conjunction. Conjunction is another name for a logical AND operation. Okay, so if you have two propositions A and B, the conjunction A and B is true if both A and B are true. Okay, so if we have two Boolean series, and we can use the AND operator to compute the conjunction. For example, we have already computed the probability that a respondent is a banker and the probability that they are a Democrat. They did that towards the end using the party ID metric. So if we need to compute the probability he's a banker and a Democrat, we should expect that it is less than probability of banker, because not all bankers are Democrats. So also banker and Democrat and banker should also be the same. Okay, so giving this into the function, he gets 0.004 as the output. Okay, so conditional probability here comes into play. It's a probability that depends on a condition, but that might not be useful. The most helpful definition. Here are some examples. Okay, what is the probability that a respondent is a Democrat given that they are a liberal? Okay, respondent is a female given that they are a banker. They are a liberal given that they are a female. Okay, so let's start with the first one, which we can interpret like this: of all respondents who are liberal, what fraction are Democrats? Alright, this makes sense also. We can compute this. So first of all, we'll get all the people who are liberal, and then we'll compute the fraction of the selected respondents who are Democrats. Makes sense. So selected is to select liberal respondent, we can use the bracket operator like this. Selected contains the value of Democrat for liberal respondent. So probability selected is the fraction of liberals who are Democrats. Um, Wait a minute, let me read this again. So what this does is, you have a Democrat list, and when you input the liberal, it only returns the ones who are Democrats, and then they are also liberals. Okay, so those all of them were given a selected list, were given into a selected series, and then the probability of selected was chosen. So this was approximately 0.52. So a little more than half of liberals are Democrats. Okay, if that result is lower than you expected, keep in mind we use a somewhat strict definition of Democrat, excluding independents who lean Democratic. Okay, the dataset includes respondents as far back as 1974. In the early part of this interval, there was less alignment between political views and party affiliation compared to the present. Okay, so let's try the second example. What is the probability that a respondent is female given that they are a banker? So first you will have all the females, and then you will choose the bankers out of them. So the probability of selected is approximately 77%. Alright. So let's wrap this computation in a function. I'll define conditional to take two Boolean series proposition and given and compute the conditional probability. So if you have liberal and you give female, then okay. So given is the thing out of which you are looking for the proposition. So out of females, how many of them were liberals? So this was approximately 28%. So now comes conditional probability is not commutative. So saying how many female respondents are liberal is different from how many liberal respondents are female. That is uh, somewhat understandable. So now this also gives us that the conditional probability of AB is not the same as conditional probability of BA. They've also given us the example. The conditional probability that you have a banker and they are uh, and she's a female is approximately 77%, while the conditional probability that you have a female and she is a banker is only 2%. Okay, moving ahead, condition and conjunction. We can combine conditional probability and conjunction. For example, here's the probability a respondent is a female, given that they are liberal and democrat. So first of all, you found all the people who are liberal and democrat, and then out of those you looked for the people who are female. So that gave you a value of 57%. So 57% liberal democrats are female. But here's the opposite thing. You were given a banker and you wanted to find out how many bankers are liberal and female. So this is now repetitive and you get an idea. So now we'll move on to the laws of probability. So in this section we'll derive three relationships. Theorem 1, using a conjunction to compute a conditional probability. Theorem 2, using a conditional probability to compute a conjunction. And Theorem 3, using conditional AB to compute conditional BA. Okay. Theorem 3 is also known as Bayes theorem. Okay. I'll write the theorem. PA is the probability of proposition A. PA and B is the probability of the conjunction of A and B. And conjunction is actually what you might also know as intersection. And PA given B is the probability, conditional probability of A given that B is true. The vertical line between A and B is pronounced given. So theorem 1. Theorem 1 was using a conjunction to compute conditional probability. What fraction of bankers are female? We are already seen one way to compute the answer. First of all, select the bankers and then use the mean to compute the fraction of bankers who are female. So this gave a Boolean list and then you computed the mean. The mean simply took all the trues as 1, false as 0, added them and thus divided it by the entire list of the length of the series. So you got like 77%. Or we can use the conditional. So first of all, you found all the bankers and how many of the bankers are female. But there's another way to compute this conditional probability by computing the ratio of two probabilities. Probability of respondents who are female and the fraction of respondents who are banker. The fraction of respondents who are female and the fraction of respondents. In other words, of all bankers, what fraction are female banker? Here's how we compute this ratio. Okay, so now a sample space is just the banker space, right? Because now we are looking for how many, what is the probability that you choose a banker and she turns out to be a female. So you'll have the sample space to be the number of bankers, while your the space in which you're interested is the space which consists of the female and banker. So that also turns out to be 77%. The result is the same. This demonstrates this result that this conditional probability P of A given B is equivalent to P A and B divided by P of B. A given B because here B was your banker and the given one is also in the denominator. So that makes sense. If we start with theorem 1, we can just multiply both sides with P of B and get this. This is also reasonable, and because P of until P of B is 0, but then I guess there would be some limits and all. This formula suggests a second way to compute a conjunction. Okay, so if we want a probability of someone is a liberal and a Democrat, that is 14%. If we use this formula, we take the probability of being a Democrat and the conditional that a person is a liberal given that they are a Democrat. Let's think about this once again. The second one in the conditional is our given. So we have a list of Democrats, and out of them we have some liberals. And you know that what's the probability of there being a Democrat. So once you multiply them, you get the same result, which is essentially this relation. Okay, this is not still as intuitive to me as the above relation because that is much more visualizable. But I guess once it strikes, it will be easy to understand. So now looking at theorem 3, we have established this that P of A and B is equal to P of B and A. So okay, using this, if we had P of B and A, it would be P of A into P of B given A. So P of A into P of B given A is P of B into P of A given B. So here's one way to interpret it. If you want to check A and B, you can do it in either order. You can check B first, then A conditioned on B, or you can check A first, then B conditioned on A. So using this, you get the relation as well. So the probability of A being true given B is true is the same as the probability of B being true given A is true times the probability of A being true divided by the probability of B being true, and that is our Bayes theorem. Okay, so they've again taken some examples. So to compute the values, so they found out the probability that someone is a liberal given that they are a banker. We've seen this value again and again. This is 22%. Then they computed the value of this portion, which was the first computed the value of the probability that someone is a banker given they are a liberal, which is the opposite. Then they multiplied it with the probability that someone is a liberal and divided it by the probability that they are a banker. It is also essentially the same. And finally, the law of total probability. In addition to these three theorems, there's one more thing that we'll need to do: Bayesian statistics. The law of total probability. Here's one form of the law expressed in mathematical notation. Okay, so P of A is P of B1 and A plus P of B2 and A. Okay. In words, the total probability of A is the sum of two possibilities. Either B1 and A are true or B2 and A are true. But the law applies if B1 and B2 are mutually exclusive. Only one of them can be true and collectively exhaustive. That means that one of them must be true. Okay, so they also span the entire sample space. So as an example, the probability of being a banker is 1.4%. So let's confirm that we get the same thing if we compute male and female bankers separately. Alright. Okay, this makes sense now. So suppose A was like your banker thing. So and B1 and B2 are two things which are mutually exclusive and collectively exhaustive. So one example would be being a male or a female. Mutually they are exclusive because in our dataset the person is either male or either female, and collectively they are exhausted because these are the only two genders which we have taken into consideration in this study. So they fit this criteria. So either one of them would be true, right? Either they would be a male or they would be a female. It's not like both of them would be zero because B1 and B2 are simultaneously zero. So this gives us a way to compute the probability. We can find all the male bankers and find the probability of someone being a male banker and the probability of someone being a female banker. And the sum would be the total probability of someone being a banker. So they've done this only and they got the same result. Okay, here's another good news that they are going to add more inclusive gender questions. Okay, so because male and female are mutually exclusive and collectively exhaustive, MEC in short, we get the same result. So applying the theorem, P of A is P of B1 given P of uh, times P of A given B1 plus probability of B2 times probability of A given B2. So this is probability of being male times the probability that the banker is. Yep, this makes sense, and you get this. So if there are more values, then you get this general summation. Also, again, we can also talk about use the political views as well. So you get like how many people are uh, associated with a particular political view. So in this scale, 4 represents moderate. So we can compute the probability of a moderate banker. That would be the probability of the person being uh, moderate. Yeah. So the probability of a person being moderate and times the probability of the person being a banker given that he's a moderate. We can also use another way to compute this, and the result, I don't think the results are the same, right? This value and this value. Um, let's just think about it. In this example, using the total, okay. So, like in the above example, we had the probability of, we are trying to find the probability that the bank, all right. So, this is the probability that the person is a moderate banker. They've used this to find the net probability of the person being a banker. So using this generator expression, they first found out what's the probability that they've shown us an example of being a moderate banker. So they also found out the probability of being the different types of political having a being different persons with like different political views, and then they summed all of them. That turned out to be the same as the probability of being a banker. So this is the summary sort of. So now let's try this. Linda is 31 years old. Okay. She majored in philosophy. As a student, she was deeply concerned with these issues and participated in anti-nuclear demonstrations, which is more probable. Linda is a banker. Linda is a banker and considers herself a liberal Democrat. To answer, it is simple, I believe. Linda is a banker should be the easier answer, because first of all we'll have a sample space of people. Out of them we'll find all the people who fit this particular spectrum. So out of these, if we impose multiple conditions, that would obviously at max be equivalent or narrow down. Okay, so first of all, the probability that Linda is a female banker, we'll find that out. For a liberal female banker, it would be the probability of her being liberal given that she is a female banker, and then indirectly we are continuously imposing more and more conditions. So as we'll see, the value is again getting smaller and smaller. Yeah. So the more conditions you impose, the more restricting it is for the sample space. Okay. What is the probability that a respondent is liberal given that they are a Democrat? Okay, so this would be. Oh, did I make a mistake here? Oh, for this one, we didn't really have to think about the conditional probability. Liberal female banker would be a liberal and a female and a banker, right? There was no. We could think of it in terms of conditionals, but here it was a simple, straightforward intersection. But here we are going to think in terms of conditionals. So this would be a liberal given that they are a Democrat, simply and Democrat given that they are a liberal. So this is the simple. I'm not going to go into the Jupyter notebook and try these out myself. but we get the idea of what we are going to do. Okay, so there's a famous quote about young people, old people, liberal and conservatives that goes: if you are not a liberal at 25, you have no heart. If you are not a conservative at 35, you have no brain. Okay, so whether you agree with this proposition or not, it suggests some probability we can compute as an exercise. So we let's okay. So young is under 30 and old is above 65 for them. Okay, so the probability of someone being young is in our sample space is 20%, while the probability of someone being old in our sample space is 17%. For these thresholds, I chose round numbers near the 20th and 80th percentile. Depending on your age, you may or may not agree with these definitions of young and old. That obviously makes sense. I'll define conservative as someone whose political view are conservative, slightly conservative, and extremely conservative. Okay, so now we have the probability of being conservative. So use prob and conditional to compute the two probabilities. What is the probability that a randomly chosen respondent is a young liberal? So that would be the probability that it is young and he is young and liberal. So this would be a conjunction, I believe. Yep, this is a conjunction. What is the probability that a young person is liberal? So this would be a conditional, I think. This would be the probability of a person being young given he is liberal, or is it the other way around? What is the probability? Okay, so this would be the probability of the person being liberal given that he is young, because our sample space is a young is the space of all young people. Yep, so this is the probability of a person being liberal given that he is young. Also, this is the first time I'm honestly trying this book out. It seemed quite cool to me, and I'm not disappointed so far. What fraction of respondents are old conservatives? This is also a simple intersection because we are talking about the total sample space here. So we'll get old and conservative as an intersection. And finally, what fraction of conservatives are old? So this would be the fraction of people who are conservative, who are old, given they are conservative. What fraction of conservatives are old? So our sample space is conservative, so given should be conservative, I believe. Yep. All right. So the first part of the book is done, and the book is honestly quite long, but it it was succinct and quite information dense. I would highly recommend going through it again. I'll also link the GitHub repo if you want to contribute, and also the book in the description.